Okay, we are starting on lecture 4 of Power Electronics and Electric Vehicles EV Drives course. So in the last class, we had talked about half-wave rectifier with a diode. So it was an uncontrolled rectifier, and we had also looked at the analysis with R and RL load. So let me try to show you some of the simulation results that based on PSIM package. So this is the diode rectifier what we have. So this is an AC source with the peak voltage of 325 volts, and it's a 50 hertz source. That is the reason you can see this is close to 325 volts here. And this is the diode, and I have connected an ammeter, and I have also connected the R and L, right, in series with this particular diode rectifier. So if you look at the voltage, this is actually the voltage, and this is the source voltage. And you can see that the voltage what we are seeing as the voltage across the inductance. So this is the voltage across the inductance. You can see that some portion is positive and some portion is negative. So generally what you would see is the volt second area that is available. That is, if I show that this is the volt second area that is available above zero. So this is from here to here, the positive area and the negative area both will be equal to each other, basically. So if we try to look at the positive area, so what we said earlier, again, let me probably come to the voltages, different kinds of voltages. So this is the source voltage, and this is the IR, I multiplied by R. So this is the voltage across the resistance. So wherever the voltage across the resistance is meeting with the voltage of the source. So we wrote this equation, if you may recall. Let me again rewrite the equation what we did in the previous class. So if we say that this is the diode and this is the resistance and this is the inductance, if I may call this as IR as the voltage drop, this is L di by dt, which is the voltage drop across the inductance. And here is my sinusoidal voltage. We wrote the equation as IR plus L di by dt equal to Vm sine omega t. So we said that di by dt will be equal to 0 when Vm sine omega t minus IR equal to 0, or resistance drop is equal to the source voltage. When these two are equal to each other, you are going to have the current peaking. That is, di by dt equal to 0 means at this point, current will be maximum. So let us try to take a look at that even in the waveform that we have shown. So in this particular case, you can see this is the resistance voltage and this is the source voltage. These two are meeting at this point, and that is going to be the point at which the current is peaking. The current peaks somewhere here, where the IR drop is meeting with Vs. So that is where the current peaks. And you can see that whatever is the difference between VR and Vs, that is the source voltage and the resistance voltage, that happens to be the inductance voltage. So here the source voltage and resistance voltage are both zero. So inductance voltage is also zero. But here the source voltage is increasing, resistance voltage is increasing, resistance drop is increasing very slowly. So the inductance voltage is also increasing here. At this point, both of them are equal to each other. That is the reason why inductance voltage is zero. And after that, you can very well see that you have the resistance voltage being higher than the source voltage. That is the reason why if I try to say Vm sin omega t minus IR drop, that happens to be negative, and that is what is seen here. So this volt times the time or second, volt second area, what is seen here, that is actually the energy given back by the inductance, and this is the energy taken in by the inductance. So the inductance stored energy will be equal to inductance, the energy given back by the inductance in an RL circuit. And the current you can see is even continuing beyond the positive half cycle. The positive half cycle is over right here. So the positive half cycle is over at this point, but still the current is continuing beyond that. So how long the current is continuing beyond the positive half cycle, the end of the positive half cycle, that depends upon mainly four factors or three factors, we can say. What is the peak value of the voltage that is available? What is the kind of resistance that is there? And what is the kind of inductance that is there? Of course, the frequency also matters, but we are assuming that the frequency is going to be a constant value. That is only 50 hertz. And that is the reason why we are not taking that into consideration. That's the reason why I said initially it depends upon four factors. But if we leave out the frequency because it is 50 hertz, still we will have L by R ratio, that is inductance and resistance, as well as voltage peak value. All these three things matter in deciding how long the conduction of the diode continues after 180 degrees. That is after the positive half cycle gets, over. So you can see that the diode, if we are looking at the voltage across the diode, for example, is going to be, if I try to look at the voltage across the diode, so this is plus and this is minus, and if I say this is Vs, which is the source voltage, so on one side it is Vs, on the other side you are having IR and LdA by dt. And when the current is flowing in this direction, initially you are going to have the resistance drop to be taking place like this. The inductance drop is also taking place like this. This is essentially when L di by dt is still positive. That is when inductance is storing energy. When inductance is storing energy and resistance drop is in this direction, the source voltage is taking care of inductance drop as well as resistance drop. Both are taken care of with the help of the source voltage. But after some time, what happens is we are having this situation where Vm sin omega t and IR is equal to each other. They are equal to each other, because of which we are not going to have any more energy being stored in the inductance. Di by dt becomes zero, and after that di by dt starts becoming negative. So once current reaches its maximum value, we are going to have di by dt becoming negative. So once it becomes negative, what will happen is instead of having plus and minus here, we are going to have plus here and minus here because L di by dt is the overall voltage. So we are going to have plus here and minus here. But if the voltage is still in positive half cycle, the source voltage is still in positive half cycle, this is going to be positive and this is going to be negative. So we are actually looking at the diode voltage across the diode. If I try to look at it, although we assume it to be zero, but there will be certain voltage that is actually appearing as voltage drop across the diode. That is going to be, if I try to look at it, this Vs and L di by dt, both of them are put together and minus whatever is the drop that is taking place across the resistance. This is going to be actually the voltage across the diode. When we are looking at once di by dt is becoming negative. So the inductance voltage drop in the sense, although it's a voltage drop, it is actually aiding in forward biasing the diode. It is aiding in forward biasing the diode. And after this, after omega t equal to pi or 180 degrees, Vs becomes negative. So if Vs is becoming negative, please note that we are not going to have this as positive and negative here. So we are going to have actually this sinusoidal voltage source is going to have positive here and negative here. This is Vs. What we are looking at is Vs. Vs is going to be positive here and negative here. So if I am writing the equation again, I should write V diode is going to be equal to L di by dt, which is actually positive, but Vs is going to be negative, and IR drop is also going to be a drain on the energy of the inductance. So this is going to be V diode. So as long as the inductance is able to overpower the source voltage and IR drop, it will be able to forward bias the diode. And that's why you see that the diode is still able to conduct and the current is still flowing in the circuit despite the positive half cycle getting over. The positive half cycle is getting over right here, but still you are having essentially the current flowing. That is why I said the overall current what you are looking at, how long it continues, that will depend upon mainly three factors. So the three factors that determine the continuity of current are L, R, and Vm values. These values are going to decide how long your current would be able to continue. So much so for this half-wave rectifier. Let us try to look at a full-wave rectifier, which is going to be in with a center tap transformer. So we will call this as center tapped rectifier configuration. So the center tap rectifier configuration looks somewhat like this. I will have a transformer like this, and I'm going to have another winding like this. So let us say this is having a turns ratio of 1:1. That is, if this has 100 turns, this will also have 100 turns. But in the middle, that is after 50 turns, I'm going to have a small tap or center tap connection. And here I am actually connecting the voltage source. So this is Vs. So what is coming up across this will be Vs divided by 2. This will also be Vs divided by 2. Now I'm going to connect a diode here, and I'm going to connect another diode here, and I will connect the load here. This is a typical center tapped rectifier configuration. So in the center tapped rectifier configuration, what happens is if it is positive half cycle, I'm going to have plus here and minus here, because of which this will have plus and this will have minus. And after all, these two windings, if I may call this as A, this is B, and this is C, and this is D. So A, B, C, D, A, B, and C, D are connected in series. So I'm going to have this as plus, this end B as minus, and again C as plus and D as minus. And we are going to have Vs by 2 appearing across AB. So VAB will be Vs by 2. And we are going to have VCD also as Vs by 2. This is how the voltages are going to be. Now, during positive half cycle, because this is plus, if I may call this as D1, and if I may call this as D2, D1 during positive half cycle, D1 is going to be forward biased. So that will be conducting. So when that is conducting, we are going to have the current essentially flowing like this. So this will be the current. So what is appearing across the load, if I may call this as some P and this as Q. So VPQ is going to be same as Vs by 2, assuming that diode drop is negligible. But under that condition, if I try to look at the voltage, this is Vs by 2. This is also Vs divided by 2. So from D to A, if I try to look at the voltage, it is Vs divided by 2 plus Vs divided by 2. So we will have a voltage of Vs here. And this is the reference point. So voltage across the non-conducting diode is going to be full voltage of Vs. But the output voltage, this is the load voltage. Load voltage is only Vs by 2, but voltage across non-conducting diode, which is D2 in this particular case, that is going to be Vs. So what I mean is if I give 200 volts here, at the output what I get will be only 100 volts. But what I'm seeing as the voltage that is coming across the non-conducting diode will be 200 volts. So it has to be rated for a very high voltage as compared to the output voltage, or twice the output voltage has to be the rating of the blocking voltage of the diode D2. The same thing holds good when we are talking about reverse half cycle. So let us say in the reverse half cycle, I'm going to have plus here and minus here, due to which again I'm going to have plus here and minus here. Because this is plus, now a current will flow in this direction. D2 will conduct. So I should say during negative half cycle, D2 conducts. Again, we are going to have the voltage, what is coming up, that is V load is going to be Vs divided by 2. But voltage across D1 by the same logic, that is going to be full Vs. So you would see that at any time when we are looking at the load voltage appearing, only one device is conducting, either it is D1 or D2. So if the voltage drop across any of the conducting diode, if we assume it to be 0.7 volts, if the input voltage is 5 volts, output will be 2.5 minus, because half of that voltage, if I say this entire voltage is 5 volts, then we are going to have only 2.5 volts coming up here and 2.5 volts coming up here. So we will have 2.5 volts that is coming up here, but out of that 0.7 is eaten away by the diode. So we will get still 1.8 volts. Rather than that, in the next circuit, what we are going to look at, there will be two diodes conducting every time. In that case, the drop will be 0.7 plus 0.7, 1.4 volts. So which means we are going to get only 1.1 volts. That is not a very good thing. If most of the voltage is eaten away by the diode, that is not a good thing. That is the reason why in low voltage power supplies, generally center tapped rectifier is used, because only one diode drop is considered. It is only coming in the conducting path. So that is the reason why center tap rectifier is preferred in low voltage power supply. And one more thing what we see is we have the transformer in the input. So there is isolation between input and output due to the presence of transformer. The transformer's presence is going to allow isolation between the input and output. But one problem that could be seen generally in this rectifier, as I mentioned earlier, is the voltage across the non-conducting diode happens to be twice the output voltage. So the output voltage is 1000 volts. The diode, which is actually blocking, which is not conducting, that has to be rated for 2000 volts. So this is definitely a big problem, especially in high voltage circuits. So high voltage circuits do not use center tapped rectifier because the blocking voltage of the non-conducting diode, which is normally known as peak inverse voltage. We call this as what is the maximum voltage that the diode has to block. So that is peak inverse voltage, or PIV, of the diode. That is twice the value of output voltage. This is going to be twice the value of the output voltage. So in high voltage circuits, especially let us say it is a 11 kV circuit or something like that, then we will require the output is 11 kV, then the peak inverse voltage will be as high as 22 kV. So 22 kV, it may be very difficult to get a diode, but 11 kV or 5.5 kV may be available. So we have to connect multiple number of them in series, which becomes very, very complex. The circuit becomes complex. That is the reason why generally we never use center tap rectifier in high voltage circuits. So let me show the simulation of center tap rectifier as well. So this is a typical center tap rectifier circuit. You can see that a transformer with 1:1 turns ratio, and here it is 0.5 and 0.5. If I say this is one number of turns, this will be 0.5 turn and this will be 0.5 turn. So the voltage will be equally divided across these two. you can see this is the AC voltage source that is connected to the primary. On the secondary side, there are two diodes that have been connected exactly similar to what we had drawn here. If you may recall, this is what we had drawn in the center tap rectifier circuit. I don't know whether I'm not able to move. Maybe the previous page. Anyway, so this is the center tap rectifier circuit. And here you can see the simulation for 3 cycles it has been done. So this is the source voltage. What you can see, red color is the source voltage Vs. And V load voltage, it is full wave rectified. Clearly, it is fully rectified. So you can see positive half cycle as well as negative half cycle. Both are appearing. Positive half cycle is appearing as it is, whereas negative half cycle is appearing as though it is reversed completely in its polarity. So if it is negative half cycle, it is also appearing as positive half cycle. And this is the load voltage. And you can see what is the voltage across the diode. Voltage across the diode is twice whatever is the source voltage. You can see the non-conducting diode voltage is twice the load voltage. And this is the load current. Load current, because we have used the resistive load, it is exactly having the same wave shape as that of the source voltage or the load voltage. And the source current is again sinusoidal in nature. What we mean by the source current is here we are looking at this as the source current. What is being supplied by the source? Whether it is D1 that is conducting or whether it is D2 that is conducting, either way, the source current is essentially going to reflect exactly what is supplied to the load. But only thing is, when diode 1 is conducting, the current is flowing in this direction from left to right. Whereas when diode 2 is conducting, the current is actually flowing, because this happens to be positive, it is flowing from right to left. So that is the reason why you see that the load current is actually, the load current is exactly in the same direction as that of the source current during positive half cycle. But during negative half cycle, the load current and source current are opposite to each other. Now, let us try to derive the expression for the voltage. So if I try to get what is the V load average value. So we said that basically, if I am looking at this as the source voltage with respect to omega t, if I just draw this as omega t, I'm going to get the current during the positive half cycle is somewhat like this. During the negative half cycle is somewhat like this. This is going to be D1 conducting and this is going to be D2 conducting. And as far as the load voltage is concerned, I will have the load voltage exactly similar to the positive half cycle voltage during the positive half cycle. And during the negative half cycle, it is going to be just inverse of this. So this is again Vs divided by 2. This will also be Vs divided by 2. Whereas Vs is going to be twice this value, because on the secondary side, the voltages are halved. This is how it is going to be. So V load average, if I say Vs divided by 2 is going to be some Vm sin omega t. So the source voltage Vs is going to be 2 Vm sin omega t. Okay. So V load average will be from 0 to pi. It is having Vm sin omega t. If I want to take it for the entire cycle, I should write again from pi to 2 pi. It will be minus Vm sine omega t, d omega t, whole thing divided by 2 pi. So whatever we are getting here, that will be the same as what we are getting here. Both of them will be equal to each other. So rather than integrating over the entire cycle, we can just integrate it over half a cycle. So I can simply say Vm sine omega t d omega t, and it has to be integrated from 0 to pi. And after that, it has to be averaged over pi. So that is essentially going to give me Vm divided by pi. And I have to write cos of omega t, the 2 minus. So because of which I can inverse the limit. So this will be pi and 0, the other way around. So this is going to be Vm divided by pi cos 0 minus cos pi. And cos pi is minus 1 and cos 0 is 1. So this is going to be Vm divided by pi, 1 minus minus 1. So it is going to be 2. So 2 Vm by pi will be the average load voltage. Whereas if I try to look at the average load current, that will be 2 Vm divided by pi R, if R is the resistance. I can even calculate the RMS value. If I want to calculate RMS load voltage, RMS load voltage is going to be starting from 0 to pi. I should write Vm square. This is Vm square sine square omega t, d omega t. And I have to just integrate it from 0 to pi and average it over pi and take the square root of this. That is what is the RMS value. Root means square, essentially indicates that I have to square every instant of the voltage waveform, take the integration interval, average it over the integration interval or average it over the entire interval over which I want to calculate the average and square root of that. That is what is RMS value. Okay. So full wave rectifier, what we talked about right now is center tapped rectifier, which is particularly used in power supplies, and it is hardly ever employed in high voltage DC, high voltage circuits. So the next circuit that we are going to look at is full bridge rectifier with diode. This is bridge rectifier with diode. So in full bridge rectifier, what we are looking at is we will have 4 diodes connected together like this. Let me call this as D1, this as D3, this as D2, and this as D4. And let me complete the circuit here. So this can have just resistance or resistance and inductance or resistance, inductance and a voltage source. So you can have multiple types of configuration. So this is the voltage source that I have connected, which is actually Vs. So when I am looking at positive half cycle, during positive half cycle, I am going to have this as plus and this as minus. And I'm going to have, because of that, D1 and D4 are forward biased. They are both going to be forward biased. So because of which the current is going to take a path like this. It will go like this. It will go, let me call this as IS. So this is going to go like this, and through the diode, it will come down through the resistance, and this is going to be load current, and this is going through T4 and ultimately returning to the source like this. So this is going to be the path for the current. So it will be from Vs positive, it will go through D1. Then if I may call this as P and this as Q, it will go through PQ, and then it will go through D4, and then it will come back to Vs negative. This is the path for the current. Okay. So if we neglect the voltage drop across D1 and D4, we are essentially connecting the source voltage positive to this positive and source voltage negative to this negative. This is how we are connecting. So at this point, I'm going to have V load equal to V source directly during positive half cycle. Rather than that, if we look at this from negative half cycle, and during this portion, because the same current IS is flowing through the load as well, we will have IS equal to IL. This is also true. During the negative half cycle, what is going to happen is this will become plus and this will become minus. So, if this plus is looked upon with respect to D3, very clearly D3 will be forward biased. Whereas the same plus is connected to the cathode of D4. So D4 will not be able to conduct, D4 will be reverse biased. Similarly, this minus is connected here and that is connected to the anode of D1. So D1 will not conduct, but the same thing is connected to the cathode of D2. So D2 will conduct. So D2 and D3 are forward biased during negative half cycle. So we will have the current going from Vs. So the current is going to go from Vs like this, and it will go through D3. And from D3, it will go to PQ. Please note PQ, again the current direction is only downward. Then it is going to go through D2. And from D2, it will return like this to Vs. So the current what is seen during negative half cycle is exactly opposite to that of the positive half cycle current as far as IS is concerned. But the load current is one and the same. So if I try to look at what is the load voltage here, V load is going to be minus Vm sin omega t. If here it had been plus Vm sin omega t, in the negative half cycle, it is going to be minus Vm sin omega t. And I'm going to have Is equal to minus IL. It is in the opposite sense. So, if I am looking at, let us say this as the source voltage, I will have actually D1 and D4 conducting until pi. 0 to pi, they will conduct. And from pi to 2 pi, D2 and D3 will conduct. And during D2 and D3 conduction, what we see across the load is somewhat like this. So this will be the load voltage during positive half cycle, and this will be the load voltage during negative half cycle. And if it is resistance load, the current will be exactly similar to that of what the voltage is. So this is going to be the current what I visualize during the positive half cycle and negative half cycle. So I'm going to have the current somewhat like this. So this is going to be I load. Whereas if I try to look at what is the I source, I load and I source will be one and the same as far as positive half cycle is concerned. But negative half cycle, it is going to be exactly opposite to that of I load. This is going to be the kind of waveform we get. And if we are looking at the average load voltage, if I'm looking at average load voltage, that the derivation will be very similar to what we had done in center tap rectifier. This is going to be 1 by pi Vm sine omega t d omega t. And we would be able to get exactly whatever is the average voltage. It is exactly similar to what we got earlier in the center tap rectifier. So this is 2 Vm divided by pi, and I load average will be 2 Vm divided by pi r. Rather than this, if we have along with resistance and inductance also, if I'm going to have R and L, if I have R and L, again, we will look at IR plus L di divided by dt. That is going to be equal to Vm sine omega t. So, this essentially is going to cause the same kind of discussion that we had for half-wave rectifier. So, when Vm sine omega t minus IR equal to 0, then di by dt equal to 0, or current is maximum. That is when the current is maximum. So, if I try to draw the waveform for this again for RL load, I have to show it as though this is my sinusoidal voltage. And I am looking at initially probably the current is starting from 0. So the current will slowly rise. And if I say that this is also IR, if R is just 1 ohm, at this point, Vm sin omega t or Vs is equal to IR. So at this point, we are going to have the current peak occurring. So this is where the current peak is occurring. So let me call this point as some alpha. So this is where at alpha, current peak occurs. After that, this is going to start declining. So I'm going to have the current start declining like this. But once it declines and reaches pi, now what happens is the other two diodes are going to jump into conduction. That is D2 and D3 are going to jump into conduction. And because of which I am going to have this voltage, what is appearing, that is actually going to be somewhat like this. This is going to be the voltage, what I see as load voltage. This is the load voltage. And when the current is declining like this, and when IR is actually again meeting with the load voltage, that is when the current minimum will occur. Again, it will start increasing from here. So you would see that the current waveform will be somewhat like this for RL load. So this is going to be current for RL load. This is how the current will be for RL load. And you would see that as far as the source side current is concerned, Until D1 and D2 are conducting, the source current is same as that of the load current direction. So IS and IL will be exactly same as each other. Only when the other two diodes are conducting, it is going to be reverse. So I should first of all draw this current as though it is going like this and it is coming down like this. And at pi, it is going to again become the reverse of whatever is the load current. So it is going to, at this point, the current is still decreasing. It is decreasing like this. And then it starts decreasing is the other way around. So it is going to decrease like this. And then it is going to start increasing. And then it will again at 2 pi. So this is 2 pi, this is pi, this is 0. So again, you would see the current decreasing and again increase like this. So this is how, with respect to omega t, the source current would be. So this is for RL load. So let me again show you the waveforms for a diode bridge rectifier. So this is the diode bridge rectifier. You can see this is the source voltage. This is the load voltage. This is R and this is L. When I have R equal to 5 ohms and L equal to 0.01 Henry, you can see very well that this is the kind of current we are having as far as our source side is concerned, and load side, it is completely full wave rectified voltage. And you can very well see again the current, source current, it is coming down slightly and then it is increasing. You can see initially the current is coming down, then increasing. Similarly, here also the current is coming down and increasing. So you can see that this is happening like this. First cycle, it is starting from 0, no doubt. But eventually what happens is at every end of the half cycle, you are not going to have the current reaching 0. The current is already at certain value because inductance retains its current. So that is the reason why we would call steady state is reached by the circuit only when I minimum in the previous half cycle is equal to I minimum in the present half cycle. Similarly, when I am talking about I max is the same across all half cycles. Compared to the present and previous half cycle, that is when we call it as steady state has been reached for the circuit. Okay. One more thing I would like to analyze is if we have RL load, that is if I am going to have R, then inductance and a battery. If I'm looking at a battery charging circuit, if I have a battery also connected, so in that case, it is as good as looking at whether this battery plays a vital role in deciding whether this diode is forward biased at all or not. So for example, if I am looking at this diode D1, it is connected to the source like this. This is Vs. So this is positive and this is negative. And on the other side, it is going to have this voltage coming up like this. And of course, inductance and resistance are there. So the cathode is connected to E, whereas anode is connected to the source. And we have to check whether these two diodes, so I'm going to have the other diode also, which is D4, and that is going to be connected ultimately to this negative. So for D1 and D4, for D1 and D4 to be forward biased, I should have Vs greater than E. Only then they will be forward biased. Otherwise, they will not start conducting. This is true when we are starting the circuit from rest. So I have to take it as though if this is my sinusoidal source and I'm going to have my voltage source somewhere here. This is going to be E and this is Vs. Then until this point, both D1 and D4 will not start conducting. Only after that, the current will slowly start. So the current will start and the same thing will be valid what we wrote earlier, that is Vs equal to Ri plus L di by dt, but plus E, because E is also opposing, because this is plus whereas this is also plus. So these two are opposing each other. So this will be the equation that is governing the current in this particular circuit. So I should say Vs minus Ri minus E is equal to L di by dt. So I have to look at actually IR, where my IR along with E also has to be added. So I should draw as though the same I, if I say this is IR may be somewhat like this. So this IR above E, where that meets with the Vs value, that is where we are going to have I maximum. I maximum occurs here. As per this equation, you can very well see Vs minus IR minus E. All of them put together has to be 0. Only then I max occurs. So the current maximum occurs somewhere here and then it will start falling. And there is a better possibility of the current falling down to 0 in this particular case compared to the previous RL case, RL load case. That is because this voltage is also opposing the flow of current. It is going to actively resist the current continuing or the inductance getting quite a lot of energy. So the same thing will hold good if I try to look at again the negative half cycle. Because the current has gone down to 0, again the current can start only from this point. So it may go like this and come down like this. So in this particular case, we are seeing again, we may have only part of the voltage appearing across the load. Overall, we may not get the entire voltage, of course, because E is also there. We may be able to see that. So what we will actually see is this will be the kind of voltage we will be seeing. And then we are going to see only E across this. Until here it will continue and then suddenly it will jump to E. And again, it will go like this. It will continue until here. And then it will jump again to E and so on. You are going to see wherever there is current discontinuity, the open circuit voltage E will come across the output side. Because there is no current here, L di by dt is 0, Ri is 0, only E will manifest itself. But if E had been really, really small And if there had been a good amount of continuous current that is flowing, if the current is not flowing, only then we are going to look at the tug of war between Vs and E. If the current is already flowing, please recall the circuit. This is the full wave rectifier circuit. This is D1, this is D4, and this is D3, and this is D2, and we are having the load here. This is connected like this. And here we have connected the voltage source. Okay. Now, if let us say the current is continuous and we are having D1 is conducting and D4 is also conducting. So they are like short circuit. So this is going to be positive and this is going to be negative. So this will be positive here because this positive will be connected to this point with the help of D1. Similarly, this negative will be connected here with the help of D4. So what you are looking at across D3 is this side is negative, this side is positive. So D3 is automatically reverse biased whenever D1 is conducting and it is positive half cycle. So during positive half cycle, if D1 is conducting, D3 is reverse biased. Positive half cycle, you will see if D1 is conducting, D3 is reverse biased. Similarly, if I am looking at negative half cycle and due to inductance stored energy, if the current is continuing and D1 is continuing to conduct, we are going to have plus here and minus here, due to which this plus will be connected here and this minus will be connected here. So you can very well see that if D1 is conducting, during reverse half cycle, during negative half cycle, D3 is forward biased. So if D3 is forward biased, you are going to see basically the D3 device jumping into conduction. Similarly, D2 will jump into conduction. Once D3 jumps into conduction, because it is a short circuit, we are going to have plus here and that plus will come up here also. And similarly, if D2 is conducting, we are going to have minus here. So this minus will come into picture here also. So D4's anode will become negative. D1's cathode will become positive. So obviously, once D3 and D2 jump into conduction during negative half cycle, with the help of D1 and D4, then D1 and D4 will be automatically reverse biased. So they will go off. That's what we are trying to say. So you will have automatically D1 and D4 aiding D3 and D2 to get into conduction, but D3 and D2, once they get into conduction, they are going to quench D1 and D4. So it is like a suicidal operation for D1 and D4. That's what happens in the case of full bridge rectifier. So here is the waveform with RL load. We already saw the RL load, and let me show with RLE. So you can see that with respect to RLE load, almost until not really 0 volt, slightly before 0 volt itself, the conduction gets over and there is no current flowing through the DC side. That is the reason you can see the open circuit voltage of the 120 volts that actually appears in the output side. Then once uh, the devices get forward biased, then immediately the current starts flowing. So again, you can see the reverse of the source voltage during negative half cycle that appears as load voltage. So you can see that very clearly. And the current is not continuous here. You can see that there is distinct period where the current is zero. So zero current period is there. Here also there is zero current period. And then you are looking at the entire current waveform looking somewhat like inductance current, what we had seen, current increasing, reaching a peak and coming down. Then it is remaining at zero for a while. Again, it is starting from zero, reaching the peak and coming down to zero. Wherever the current is zero, that is where you would see very clearly the DC source E manifesting itself across the load terminals. So this is with an inductance value of 0.01 or 10 millihenry. Whereas for the same resistance with a smaller inductance value, that is R by L or L by R ratio decreases, then correspondingly the conduction takes place only for short while. Here the DC voltage E appeared across the load for this much, whereas here it is appearing for much larger period of time. That is because we are having lower inductance, the current will come down to zero quickly. So as we mentioned earlier, we always see that the value of R, L, and the peak value of voltage, all of them, peak value of source voltage, all of them influence for how long your current in the load circuit is sustained. So the current sustenance depends upon mainly three factors. One is inductance, the second one is resistance, the third one is what is the value of the source voltage. If we are having the DC also, that is the battery charging kind of circuit also, that is the DC voltage source is also connected on the DC side, then we are going to have even that influencing how long the current is sustained. Okay. So in the next class, we will look at controlled rectifier, and before that, if there are any faults, if one of the diode conks out in a full wave rectifier, how it is going to behave. We will take up those things in the next